Hi, everybody. Can people hear me? I'm going to go ahead and share my screen. Just so you know, there's a question and answer bar in the bottom if you'd like to click on that. You can ask questions along the way. You can also click to raise your hand if you want to raise your hand, and I can either ask you a question, you can type it in, or I can also make your microphone go live. And if you want to use your microphone, you could just ask your question out loud as well. So let me go ahead and share my screen. All right, everybody. So this class is just going to be going for 2 weeks. And I'm hoping that we can just provide a resource. I'm going to go over really common questions that are going to show up on the test. And we're just going to go from there. Let me know if you have any questions along the way. So today we're going to be covering as much as we can of Unit 1. We're going to talk about different limits. We're going to talk about evaluating limits from graphs, using tables. I've come up with a bunch of questions that you may or may not see when you take the test in a couple weeks. And then if we have time, we're going to cover a little bit of Unit 2. We're going to focus mostly on the conceptual stuff today. And then maybe in the following days, we're going to do a little bit of calculation. So I'm going to try this thing and see if it actually works. We're going to do a pop quiz here. And let's see if I can make this poll work. I'm going to launch this poll. So I have this thing on the screen. It says pop quiz. If the limit as x approaches 2 of f of x is equal to 5, then f of 2 is equal to 5. Is that true? Is that false? Go ahead and vote. Oh, that's exciting. It's actually working. That's kind of cool. Okay, so I see that most of you voted false. And that's true. That's one of the things that we want to talk about today. So the limit is different from something, from the actual value of a function. And you want to keep that in mind as we go through some of the questions. So I hope that whoever chose true accidentally misclicked. All right, let's see if I can do some more of that. This was just like my first experiment. This is my first time teaching something live on Zoom. So I figured, oh, might as well try to use some of the different features it has. So this is a very technical definition of a limit, just in case you get a free response and have to justify something about a limit. So we see that the limit as x approaches c from the negative side, right? So that's like, let's say we have a number line here and this is c, and then this is my graph over here. Remember that this little negative sign says we're approaching from the left-hand side. And if the limit as something approaches from the left-hand side is equal to the limit as something approaches from the right-hand side, then that's when the total function is going to have a limit. And as we discussed, that's not necessarily what's going to happen if we have the value of a function equal to a certain number. So this is the most common type of question that you might see on the test. You might have a rational function here. So the first step you want to do is, whenever you have a rational function, go ahead and try to factor it. So if we try to factor right here, what do we get? We get x plus 3 on top, x plus 1. And then on the bottom, if we factor that, we get x minus 4. And then we get x plus 1 as well. And notice magically over here that these two will cancel out. However, we're not going to cancel them out right away. We're going to evaluate the function first. If we plug in -1, what do we get? We get 2 on top. That's -1 plus 3 times 0 over -5. And we plug in that -1 over there, we get 0, right? So whenever you get something divided by 0, that does not exist. You cannot divide by 0. So the function value at -1 does not exist. However, we can evaluate the limit. Now that we've factored it, we can simplify the function to be as if x is equal to 3, x minus 4. But I'm just going to put this little reminder for myself that x cannot equal -1, because that is a domain error in the original function. And now we can evaluate this by plugging the limit into our new function. And so we see that as we approach from the left-hand side, -1 + 3, -1 - 4, we get +2 over -5. So the limit as x approaches 1 from the left-hand side is -2/5. And it'll actually be the same if we plug in -1 here because there's no discontinuity. So therefore, because b has a limit value of -2/5, and because c has a limited value of -2/5, then we can say that d will also have a limit of -2 over 5. Stop there. Does anybody have any questions? Feel free to raise your hand if you'd like to. Okay. Go on to the next slide. This one. So whenever a question asks about continuity, you want to have this in mind. Oh, and then something that I do want you to note, I've shared a Dropbox link with all of y'all, and you should have all the worksheets available. I've tried to highlight the most important parts of the worksheets. So what I would love for you to do is actually to take some of these concepts that I'm highlighting and put them on your own version of a cheat sheet. Remember that the exam this year is going to be open book, open note. Obviously, you're not going to have a 500-page book there and start flipping through it because you only have 45 minutes to do it, right? So I'd love for you to consolidate some of these notes into like 2 or 3 sheets of paper. And then you can have that as a resource for you as you're typing up explanations. So if a function asks you, or if a question asks you about continuity, you want to think about this definition that I have highlighted right here, right? You want to make sure you note that the limit as you approach from the left-hand side is equal to the limit as you approach from the right-hand side is also equal to the value of the function itself. So you have to prove that all 3 things are equal to show continuity. So for example, if I wanted to show continuity at x is equal to 2 for this function, I would have to, let's plug in the number 2 first. So 2 cubed minus 4 times 2 over 2 squared plus 8 times 2 minus 20. And if you notice on the bottom, 2 squared plus 8 plus 2 is 16. 16 minus 20 is divided by 0, right? So when you divide by 0, that's undefined. So then this one cannot be continuous, right? But what about at x is equal to 0? Let's try that. So we get 0 cubed minus 4 times 0, 0 squared plus 8 times 0 minus 20. Now we get 0 over -20. Well, 0 over something is just equal to 0, right? So we can say that h of 0 is equal to 0. So we know that the value of the function exists. So now let's see if the limit exists. Well, the limit, if the value is there and then there's no point of discontinuity, we could say that the limit as x approaches 0 from the left-hand side is also equal to 0. And then we can also say that that's equal to the limit as x approaches 0 from the right-hand side of h of x. So you would have to write out something like this if the question asks you about continuity to get full credit. Any questions about that? Okay. So since we're talking about continuity, let's see if I can ask this second poll question. Poll question number 2. We're now going to talk about discontinuities. So this one, you can choose multiple ones. Can you all think of the different types of discontinuities off the top of your head? I almost feel like I'm watching an election or something. You can kind of see the bars swinging back and forth. I'll wait a couple more seconds. Feel like a couple people aren't paying attention maybe. I don't know. We'll see. So here are the results. If this were a popularity contest, infinite discontinuity would have won. So most of you got them right. Some of you got confused. Some of you chose cusp. A cusp actually isn't a type of discontinuity. A cusp occurs when you have a graph that has like a kink or a corner. So like here would be a graph, right? And then this would be a cusp. But if we think about the definition of continuity, visually speaking, a graph would be continuous if I could draw the whole graph without picking up my pen or pencil, right? And a cusp, you can still draw it without picking up your pen or pencil. So a cusp is still continuous. So this is the definition of a removable discontinuity. Let me get rid of this graph and draw a removable discontinuity graph. A removable discontinuity would be is like if you drew a graph and then all of a sudden there's this hole in it. So hole's like the more common way of saying removable discontinuity, and it looks something like that. You could also have a removable discontinuity graph with that, and then there's like a dot somewhere else. So that would be two examples of a removable discontinuity graph. And so what's the definition of removable discontinuity? That's when the limit exists and approaches a specific number, but either the value is undefined or the value does not equal that. So this would be an example. Let's say this is 1, right? The limit approaches 1, but maybe the value of the function is equal to 3. I got a question that says, can we be attendees? Are you going to be posting the notes in with the markings in the Dropbox as well? Yeah, I'm more than happy to upload the markings that I've done after I'm done with it. Absolutely. And then can we make them be attendees? Was there something specific that you wanted to ask, Rose? Because I'm not sure how to do that right now. I might be able to do it for future lessons, but I won't be able to do it for this specific one. You would like to add to the equations. The way I'm doing this right now is actually other people can't annotate because I'm using, I'm actually using Notability to write down everything. Feel free to send me a message. I'll post my, oh, okay. Let me make you live then so you can say something really quick. Let's see, Rose Dawson. You had a question, Rose? You there, Rose? Hello.
Your dick will slide on my pussy tonight.
Okay. That's, let me kick this person out. Okay. I think we just got Zoom bombed. That's awesome. Anyways, back to the subject at hand. Let's, you could get a piecewise function. So whenever you get a piecewise function, pay attention to the boundaries of the function and notice for a, right, it says f of 2. Now, when you get f of 2, you actually can't plug this into the function because it's not included on the right-hand side of the function. Okay, so this one would be an example of f of 2 does not exist. Versus here, if it asks you to evaluate the function as you approach from the left-hand side is when x is less than 2. And then you can just go ahead and plug it into that function. So the limit as x approaches 2 from the left-hand side will equal 2 squared. And that's equal to 4. And it's okay that the function value is not included. The limit does exist. And similarly, if we want to do the right-hand side, we can plug in 2 on the bottom equation because 2 plus means we're going to approach from the right-hand side. So we plug that in, we get 2 times 2 minus 1, and we see that that's equal to 3. And so we've shown the limit from the left is 4. We've shown the limit from the right is 3. So then we can say that the limit as x approaches 2 of f of x does not exist. Why? If a question asks you why, because the limit as x approaches 2 minus of f of x does not equal the limit as x approaches 2 plus of f of x. Any questions so far? Alrighty. So then, just in case anyone wanted the definition of a non-removable jump discontinuity, we have this definition here. I don't think that you need to know this definition. You just need to know that a jump is a type of discontinuity. So please keep that in mind. Let's work through this example though, just to show, find the values of a and b such that a function is continuous when x is equal to -1. So what we're gonna do is we're gonna use that limit definition. So we're gonna find the limit as x approaches -1 minus of this function. So -1 minus means we're gonna plug it into the top. And when we plug it into the top, we get a of -1 squared minus b. So the limit from the left-hand side is equal to a minus b, because -1 squared is just +1. We can do something similar by evaluating the limit from the right-hand side. The limit of -1 plus of f of x. So then we go 2a -1 plus b is equal to -2a plus b. Right? And then we want to do the third part to finish the definition of continuity. We know that f of -1 is equal to 4. So that means if this function is continuous, or we want it to be continuous, these three things all need to equal each other. So then we can set up a system of equations. We can go a minus b is equal to 4. And then we can go -2a plus b is equal to 4 as well. And then solve that way by doing elimination. We'll just add these two equations together. A plus -2a is -a. -b plus b is nothing. 4 plus 4 is 8. So a is equal to -8. That's one of our answers. And then we can plug -8 into either one. I'll plug it into the top. We get -8 minus b is equal to 4. -b is equal to 12. B is equal to -12. So my solution set is -8 for A, -12 for B. Any questions? Why didn't I use substitution? They're both equal to 4. I didn't use substitution because I was just trying to reiterate the idea of like, you need to show that you have the limit on one side, you need to show that you have the limit on the other side, and then you need to show that you have the value of the function when x is equal to -1. And if you are able to show that, then you'll get full credit on the test, versus if you just directly substitute it on the test, your work may not be absolutely clear, so you may miss out on a point that they're going to award you, right? The AP standards have a very strict guideline of what it means to be continuous, and I want to make sure that if you do get a continuity question, that you can show that. And then you have it reiterated, right? If a function is continuous, then the function and the limit are the same at that point. Just remember that if you get a continuity question. Can a jump continuity be shown with this equation? Absolutely. So in this particular case, when a is equal to -8 and b is equal to -12, then the entire function would be continuous. That means I could draw without picking up my pen. But if a and b were some other values, then there would be jump continuities. it would be a disconnected function. Maybe it looked like this, and maybe there's a point here, and maybe it looks like that, right? We won't know exactly because, you know, A and B could be infinite different values. Good question so far. Okay. And then finally, we have the infinite discontinuity, right? So infinite discontinuity is just the fancy way of saying vertical asymptote. And you just need to know that these are the different ways you can write vertical asymptotes, right? You can approach it from the right-hand side, or you can approach it from the left-hand side. And they're either going to approach positive infinity or negative infinity, right? And only one of these needs to be true for a vertical asymptote to exist. I highlight this example 12, but the process of example 12 is exactly going to be the same as some of the one I just did. So the idea here is, in order to show continuity, you just need to plug in the number 2 into this function and set it equal to k. And then let's just do part A, just so y'all can understand the idea behind vertical asymptotes. When I see this notation, I'm thinking of a vertical asymptote because it can only approach it from one side. So whenever you see this, you want to try to factor it first, right? So this one factors into x plus 3, x minus 2. And then on the bottom, this is a minus 2 right there. So that means it has to be 2 and 1. This one's the bigger one, so that's a minus 2, that's a plus 1, 2x, and this is going to be ax. And notice magically, right, we erase that because they factor out, and then I know that x cannot equal 2. I guess that's why they have that there. Right, so we know that that's a removable discontinuity. One thing you want to remember is when you can factor something out like that, you get a removable discontinuity. And then let's evaluate the limit as we approach -1/2 from the right-hand side. Well, I would think about it this way. When I approach -1/2 from the right-hand side, I'm going to plug in a number that's slightly bigger than -1/2. When I plug in a number that's slightly bigger than -1/2, let's say -0.49, maybe, then I'll get a slightly positive number on the bottom of the denominator. And then when I plug in -0.49 here, I just get a positive number. When I get a positive number over a really, really, really small positive number, essentially my limit is going to approach infinity. So that's kind of the thought process I have when I'm trying to evaluate an infinite limit. Any questions on that one? Let's move on to some of the properties of limits then. So I don't think you need to write this down. This is just there for your reference though. But basically, if you have limits, they just obey all the laws of addition, subtraction, multiplication. There's nothing tricky here. So literally, if you know your limit, you can just plug it into any sort of equation. So that's there for your reference in case you wanted it. I did want to go over something like this, like giving you a graph and then evaluating these limits. So let's try part B. Right, B says evaluate the limit as x approaches -3 of this weird looking thing, right? Well, with x squared, when you're evaluating a limit, you can just directly substitute into that x, right? So that's easy. Let's figure out the limit of g of x though. So the limit of g of x as x approaches -3. Let's see, so here's g, right? And then here's where x is -3. This one's nice, right? There's not a discontinuity. They both approach the same value here. So the limit of g is equal to 1. And let's do the limit of f of x, and let's figure out what that is. The limit of f of x as x approaches -3. That one is here. That's nice. They approach -1. So once you do that, you can just plug everything into the equation, right? So you can go -3 squared. The limit of g is 1, and then the limit of f is -1. And so overall, you just get the answer is -9, right? That one can be done using direct substitution. I'm going to let you ponder part C, though. I'll give you a minute to do that and type in your answers into the chat box. Yeah, I already see that a couple people are answering 1, right? So what we want to do is we want to evaluate the limit of f of x first, right? So we find f of x, which we found from the earlier question, right, is -1. And so then basically we can do a direct substitution to that and find the limit as g approaches -1. The limit as g approaches -1 is just going to be +1 right there. Limit of g of x as x approaches -1. I want to be very clear with my writing because I want you to be clear when you actually submit your writing to the AP. All right. Just want to really, really quickly go over the squeeze theorem. It's not hard. It may show up. What you're going to see is you're just going to see a three-way inequality, right? You have one function is less than or equal to another function is less than or equal to the third function. And if this is squeezed between them, in order to show the limit, you just need to show the limit of the two sides of the function here. Right, so like if you were to write this out and do it the way they want you to do it on the calc exam, you do limit of x of 1 if -3x approaches -3 times -1 is equal to 3. So the limit on the left side is 3. We're going to do the limit on the right side, and I'm just going to skip it, and I'm just going to tell you that it's equal to 3. And so if you're going to write your explanation on the test, you need to say that the limit as x approaches -1 of g of x is equal to 3 because Squeeze theorem says, Squeeze theorem, that if, right, and then you want to put the whole statement there, that if this statement is true, just copy it there, and if this limit is equal to 3 and that limit is equal to 3, then g of x, the limit of g of x is equal to 3. You need to be a little bit redundant like that just to make sure you're showing that you're understanding what Squeeze theorem is saying, right? So notice the two statements, they're bolded with the if, right? So you want to start off with if this is true and if that is true. You need to have those two conditional statements be true in order for you to use Squeeze theorem. So definitely, like if you want to take a screenshot of the notes, if you want to write it out, just in case you see a squeeze theorem. There was actually a squeeze theorem question on the AP exam last year. Alrighty. Next thing. I want you to be careful if you do see a one-sided limit on the test, because it can be a little bit tricky. So let's look at number 8, for example. We want to find a one-sided limit of a composite function. So what do we need to do first? We want to approach -3 from the negative side of g of x first, right? So g of x here is presented in the graph above. So what happens as we approach -3 from the negative side? When we approach -3 from the negative side, that means we're approaching the number 1. We're approaching 1 from the negative side, though. So then we can evaluate the limit as x approaches 1 from the negative side of f of x. Whereas f of x is a little bit further above. Scroll so you can see it. And now we can approach 1 from the negative side, right? So as we approach 1 from the negative side, oh, it should be -1, excuse me. -1, -1. So we approach -1 from the negative side. As we approach -1 from the negative side, look, here we approach 0. So the answer to this one is 0, okay? How could this have been different? Let's imagine that this graph didn't go this way and it actually went something like this. This would have completely changed our answer with a one-sided limit. Okay, if we approach -3 from the negative side, we would have approached -1 from the positive side. Let me change my colors so to show that there's a little bit of a difference. We would have approached -1 from the positive side, right? And if we approach -1 from the positive side, that's going to look like this. We're going to come in from there. So if we had done this and had a slightly different graph, we would have had the limit be equal to -1. So that's something I definitely want you to be careful of in case you get a one-sided limit with a composite function. Okay, and then one more type of question is you could get a one-sided limit with this weird like product function here. This one shouldn't be as hard though, so I'll give you a second and see what you get there for number 9. Type in your answers into the chat box, please. I'll make this pink for the notes, just so y'all can see. This is pink, pink, pink. Interesting, I'm getting some discrepancies for this one. What do we got? Well, what is g of 1? Well, g of 1, if I were to plug it in, g of 1 is just equal to -1, right? So g of 1 is equal to -1. And then what do we have? We want to find the limit of x as x approaches -1. Well, that's easy. That's just -1, right? And then we want to find the limit of f of x as x approaches -1. The limit of f of x as x approaches -1, oh, plus, can't forget my plus sign. The limit of f of x as x approaches -1 from the plus side is equal to -1. And then we can just compose them all together into the equation then, right? So we get -1 plus -1 times -1. So that's -1 plus +1, that's equal to 0. This one's also 0. Don't you love calculus? They have you do all these like derivatives and integrals and stuff, and then your final answer is just 0. Okay. So that's just graphical in case you get a graph and they ask you to evaluate the limit. I wanted to make sure you knew how to do that. The next part is limits at infinity. Lazy 8. Okay. So I've noticed that this is a concept that a lot of students forget. The definition of a horizontal asymptote is actually this or this, or I like to think you have to evaluate both sides. I've actually seen this on a free response question where they ask about horizontal asymptotes, and then most students would do this side, but then they'd forget this side. And by forgetting to do that side, they actually docked a point. It was a 2-point question, and they gave you a point for doing the limit as x approaches positive infinity, and they'd give you another point for x approaches negative infinity. So something to keep in mind. Please keep that in mind if you get a horizontal asymptote question. Another type of weird function here. Okay, so y'all should be decent at doing horizontal asymptotes. So what we want to do is we want to look at the degree of the top and of the bottom. Well, what's the degree of the top? The degree of the top is just the first degree function, right? So we could say the limit as x approaches infinity of f of x is essentially equal to just 4x, right? Because the 2 is much smaller than the 4x when we're talking about positive infinity. And then on the bottom, it would just be essentially equal to root 9x squared, right? Because this x squared and this 1 are of lower degree, so they're not going to affect the asymptote as much, right? So actually at infinity, they're not going to affect it at all. So as x approaches infinity here, since x is the same degree as x squared, the limit at positive infinity is just going to be 4 over root 9, which is equal to 4/3. Yeah, that's just the limit there. Now, what happens when we approach negative infinity? So this is the tricky part. Whenever you have a function that is the square root of an even power, that's essentially saying we're going to do I'm just going to factor out that square root. And then the square root of x squared is basically the absolute value of x. Think about that. Like when you have an even powered exponent, if you plug in a negative function, that's actually going to make it positive. So even if we were to plug in like -10, -100, negative infinity, it end up being a positive number there. So at negative infinity, the top is going to be negative, right? Because we have 4 times a really, really large negative number. Let's just type in 1,000 as a placeholder. And then on bottom, it's going to be root 9 times 1,000, essentially, right? So then at the bottom, it's going to be -4/3. I see a bunch of questions lighting up. Let me. So keep this in mind when you get the square root of a square. So in each of these instances, you're actually going to have a graph that has 2 different asymptotes, right? So one is a positive version maybe, so it looks something like that. And then as x approaches negative infinity, you're going to have something that looks like that. Any questions? Okay, and so this is going to be very useful for BC students, but it should be helpful for AB students too when you're thinking about exponents. Think about this as the order of increase or the order of decreasing. So you have sine of x, which is the smallest function, right? And then you have k, which is some sort of number. And then you have log, and then you have any exponent, and these go in order, right? So x to the first is smaller than x to the second, is smaller than x to the third, right? Et cetera, et cetera. And then you have your exponents, and you have your factorial, and then you have this one, which is your power function, when you have x to the x. And so this should help you with the intuition when you're evaluating limits at infinity. So for example, if you look at a, right, you have this 1.01. This 1.01 looks really small, but actually it's an exponential function, and exponential functions always grow at a faster rate than these polynomial functions. So this limit will be like, will be 0 because we have a bigger denominator. Yes, Alita asked, this will be helpful for series, right? And absolutely, this will be definitely helpful for series because you're gonna have to do either ratio test, you don't have to do comparison test, but maybe for ratio test. You do have to show your work when you get to series, but at least it'll help you develop the intuition of you should be getting 0. Similarly for part C, right? Ln x is a very, very weak function. It's weaker than a cube root function because x, the 9th root, not cube root, the 9th root is just x to the 1/9 power, right? So that falls under this x to the n category. So this one will also be 0 because logs are weaker than polynomials or radicals. And then hopefully you can see both of these, right? And if we do the comparison here, you're actually going to have to do the ratio test if you have series in BC, but this one is also going to approach 0 because x to the x outpaces x factorial. And then conversely, if we have the bigger one on top, you're going to approach positive infinity in this case. So that's just kind of a shorthand way of showing the limit that exists without having to actually do it. And then finally, I want to do these really quickly so you just remembered a couple of these things. So if you have exponential functions, these are kind of like degrees, right? So these would be the same degree as x approaches positive infinity. So these are these are increasing at a rate much bigger than 8/4. So you could just do the ratio test over here. So the limit here would just be -1/1. Versus for part B, if we're evaluating the limit as x approaches negative infinity, then we just have to do this exercise. And I hope that y'all remember that when you have an exponential function and the exponent gets incredibly small, your limit approaches 0. Or your limit does not become a negative number, does not become negative infinity. Your limit approaches 0. So in this case, we can do direct substitution with our limit. The limit is 8 minus 0/4 plus 0. The limit is equal to 2. Questions about that one? Alrighty, let's see what I have next. So we've done our infinity. We need to do our algebraic limits now. So if you use this sheet, you can kind of see the different methods you have in case you ever get a limit question. So always, always, always try direct substitution first, right? If you can plug in the number, then the limit does exist. So we don't even need to do A or B because I don't think you'll need to know how to do cosecant, right? This is a non-calculator test, so don't worry too much about that. However, you should know when a vertical asymptote exists, right? So this is when you get a number that's not 0/0. Don't forget that these things over here are your indeterminate form. So indeterminate does not mean 0, does not mean undefined. Indeterminate means for your limits, you have to do some extra work. That's why they're called the bad guys. So let's do part B of example 2. So this one's saying, let's evaluate the limit as x over sine of x approaches pi from the positive side. So on the top, that's pretty easy, right? On the top, if we do direct substitution, it's just pi, that's a number. On the bottom though, we get sine of pi if we do direct substitution. Sine of pi is equal to 0. So I guess the question is, it's going to approach infinity. Which infinity is it going to approach? There's a couple ways you can do it. One is you can really quickly sketch out the sine graph. Right? And then you know that sine graph should look like something like that. This is 2 pi. This is pi over here. And this is 0. And if we're approaching pi from the right-hand side, we're going to go this way. Oops, that shouldn't have been a triangle. That should be an arrow. We approach pi from the right-hand side. So that's basically saying that we're going to have a very small negative number. When you have a number over a small negative number, then your limit approaches negative infinity. Another way you could do this, if you're not comfortable with the graph of sine or graph of cosine, you could literally plug in, instead of 3.14, you like plug in this and you go plug in sine of 3.15, because you know that's slightly bigger than pi. And then you see that you get a negative large number, assuming that your calculator is in radian modes. If you're gonna have to use your calculator to evaluate some sort of trig function on the test, make sure your calculator's in radian modes, otherwise you'll get a really, really weird answer. Example 3, you could get limits at infinity, so we kind of gone over those. Usually it's pretty easy with this ratio test, so that one's just -5/4. Piecewise functions, we've already done that, right? So we just make sure that the value of both sides equals the same thing at that limit. Squeeze theorem, we've also gone over. Factor and divide out, right? That's going to be the biggest one that I see all the time on the test, right? You get 0 over 0. The easiest way is to factor if you can. This one you can do synthetic division, but can any of you think of a maybe a simpler way of doing this one that I will talk about more later instead of doing synthetic division? Because I don't think you need to know how to do that. Factor it by cubes, sure, you can do factoring by cubes. I feel like a lot of people don't remember how to do that though. But yes, absolutely factoring by cubes. Can anybody else remember another way from their calc class? Hospital, yes, l'hôpital. So in case you get something weird like this and you get 0 over 0, think about l'hôpital. Good. I'll make this note so in case people want to see my Le Hospital. I used to think that there wasn't an S in his name, but it's just that French people don't pronounce CS. Who knew? Oh, and then the O has a weird hat on it too. There. Now I'm factually accurate. And then this one's the hardest one, or the most tedious one. If you get radicals in a rational function, just remember to multiply the top and bottom by the conjugate. I guess you could use L'Hopital's rule here too if you wanted to. For example, on the first one, if we want to evaluate the limit as x approaches 0, first off, we get 0 over 0, right? So then what we do is we take the part with the radical, and then we make sure to multiply it by the radical part plus, by the radical part plus that number, okay? And then we do that because when you FOIL it out, the middle terms will cancel. So then let me go back to purple because that's my color. We go x plus 1, then you get the plus rad x plus 1, you get the minus rad x plus 1, right? They cancel. Bye, 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 bye. Minus 1. And then on the bottom, when you get to that point, do not FOIL out this x. That's going to make things very, very gross. Okay, we get that. Look at the top, we get x plus 1 minus 1. So we just get x on top. And lo and behold, right, that x is going to cancel out with that x that we didn't distribute. This one wasn't too bad, but I've seen harder ones. So then you get what? 1 over radical x plus 1 plus 1. And now we can evaluate the limit as x approaches 0. And when we do that, what is that? 1 over 1 plus 1, 1/2. Most complicated way of getting 1/2 ever. Cool. So that is a trickier example that you might have to do. You can always use L'Hopital's if you want to. And then for any of you following along the worksheets, You don't need to really, I don't think you need example 8. I don't think you need example 9, sledgehammer. If you have L'Hopital, you don't have to sledgehammer any of this. Or if you know your definition of derivative, which hopefully we will get to today. Show library. Okay. Let's move on to our continuity. We've had this discussion. Let me get rid of this thing first. We have our definition of continuity over there. You're not going to get a crazy piecewise function like this. Where did I want to get to though? Oh, okay. Something for you to think about in case you need to know this. These things are all continuous by definition. As long as it's on their domain, all these things are continuous. Because for a lot of your justification arguments, you need to say because the function is continuous. So I've highlighted that for you there. That's why I have the sheet. Okay, this one's for IVT, the intermediate value theorem. So this is another one. There's like maybe 5 theorems that you just want to have on your paper. I'll read this out loud and then I'll give you an example because this weird definition is kind of weird. Right, so it says if the function is continuous on a closed interval, then f of x takes on every value between f of a and f of b. Put differently, if we know of a y value, say y is equal to u, that resides between the two y values of the two endpoints, f of a and f of b, then we are guaranteed at least one value c between the endpoints that generates that y value such that f of c is equal to u. And that's really complicated. Basically what it's saying is we're starting here and we're ending here, and we know that our function is continuous. We're gonna have to cross through this point at least once. Honestly, we could cross through like 1,000,000 times, right? But we're guaranteed at least one. Otherwise, you'd have to pick up your pencil somehow. Right, so that's your intermediate value theorem. How do you apply it? Let's go to a question. I'll let this stick here for a second if anybody wants to screenshot, but it's in your notes, right? This is on 1.5. So the question I have is this. This was actually from the 2007 FRQ. And then they give you this weird table. And then they give you this conditional statement. It says f and g are continuous. So they give you these x values. So let's go ahead and plug in those x values into our function. So let's do f of h of 1. H of 1 is equal to f of g of 1 minus 6. Okay, so if we want to figure out what g of 1 is, this is how we read the table. G of 1 means we're going to go in here, and then we go over to this. So this is telling us that g of 1 is equal to 2. Right, so then we can go ahead and replace this g of 1 with the number 2. So we get f of 2 is equal to, I don't want to do is equal to yet. I want to do minus 6. And now I can figure out what f of 2 is equal to, right? So if f of 2 is equal to 6, I'm going to go to 2 in the table, figure that that's 9, right? And so I get that's 9 minus 6 is equal to 3. So I did the first one. Why don't you all help me figure out what h of 3 is now, right? Because we need to figure out what that is equal to. Yay, -7, right? So h of 3 is equal to -7, good. And so how do we set up IVT then? So you need to say, because you need to show continuity, right? because f of x and the weird thing about notability is if you hold your pen too long, it starts like making shapes. Because f of x and g of x are continuous, I'll do cont for continuous, then h is also continuous. So we've shown continuity. And then we can do a three-way inequality. We can say that -5 is greater than or equal to h of 3 and less than or equal to h of 1. Right, so we need to show this second part, right? We have two conditional statements. We showed continuity and we've shown the y values are on the closed interval. Make sure that it's a closed interval. Then you can say intermediate value theorem guarantees, how do you spell guarantees? Guarantee. What a weird word. And then you can literally just say that statement. Guarantee that there must be a value r. And you can use this symbol if you want, between 1 and 3. Such that h of r is equal to 5. And that's how you get the full credit on a free response if you got this question. Anybody is curious, this little pitchfork thing is that there's an x between 1 and 3. You could also do inequality notation if you want to. Any questions on this continuity question? What is the mean value theorem? We will go over the mean value theorem later, but it's the same idea. The mean value theorem, we're going to use it with slope, but we're just focusing on continuity right now. Are there any other theorems involving continuity that we need to know? No, you just need to know intermediate value theorem. And the wording will be something like that, right? So show that there's a value of the function. So when you get into the other theorems, they're not going to have h of r, they're going to have like h prime of r or something. So they're going to have a derivative there. So the only one that deals with continuity is intermediate value theorem, just IVT. And I guess if you need to know, it's also all the definitions, right? Just to make sure you're getting full credit. Okay. So then we have this question right here. I'll read this question out loud and then I'll answer this question that I just got. So can the intermediate value theorem here be used to prove that f of x is equal to that big number somewhere on this interval 2 to 4? So type in yes if you think it can be, or type in no if you think it can't be. And let me read this question. And so Anna's asking, do you think that theorems questions will be on this year's exam? I absolutely think that theorems questions will be on this year's exam, at least for some part of it, because theorems you can look up, right? But then you'd have to apply it specifically to the question as they're asking it. So you can always look up the theorem on Google, but being able to respond to the really, really weird question they're going to give you is likely going to be a case instead of just like plugging numbers into your calculator, right? There's probably going to be tons of letters on the test this year instead of actual numbers. So I get an argument here. Some people think yes, some people think no. And so this one is actually no. So the reason is that we need for the y's to be a closed interval. What is the minimum y value there? I don't know. Let's say, I don't know, -3. I'm just going. So we can say if the y values are greater than or equal to -3, less than equal to positive infinity. So because the upper bound of the range is unbounded, we cannot use the intermediate value theorem. The intermediate value theorem says that the y value has to be less than or equal to f of b and greater than or equal to f of a. Okay, so just remember that it needs to be bounded. Obviously, since there is an asymptote, it will pass through that point. We just can't use the IVT to prove that. Must be bounded on both sides. Bounded. How about number 4? For that function, does IVT guarantee such u that u is between f of 4 and f of 10? This one is no. Remember that there's 2 conditional statements that you need to show for IVT. Number 1 is continuity. So let's check continuity first. If we want to do continuity, then we need to plug in 4. Where do we plug in 4? We plug in 4 into the top, right? And when we plug in 4, f of 4 is equal to 4 minus 2 squared, which is 4. And now let's do the limit as x approaches 4. Doesn't matter, from negative. Let's do the negative side first of f of x. And as we do the negative side, that's equal to 5, right? And if we approach it from the positive side, it's also equal to 5. So we cannot use IVT here because it's not a continuous function along that interval that they give us. Okay, so you need to prove 2 things when you're doing IVT. Number 1 is continuity, and number 2 is you need to know that the boundaries are bounded. Questions? Okay. That's all I wanted from that worksheet. We have time for some of this tangent line stuff that I wanted to go over. There's just a couple things that I want to go over from tangent lines. Tomorrow we're going to go into more like the tricky derivatives and stuff. But I wanted to point this part out on page 4 of the notes for 2.1. I just want you to be familiar with all the different ways of wording tangent lines and secant lines, right? So everything on the left is average rate of change, f of b minus f of a over b minus a, or slope of the secant line, right? So they can ask you the same thing in 3 different ways. And on the right side, they can ask you the same thing in 5 different ways, right? The slope of the tangent line, this limit notation of derivative, right? The derivative at c, actually using the function form and saying it, or IROC. I call this IROC. And then we have AROC here. So that's just kind of my shorthand notation of talking about average rate of change or instantaneous rate of change. So that's on page 4 of the notes for 2.1. I also want to point out that there's this form of the limit too. So you just got to remember that this part is the slope, right? So if you have this part as the slope, and then if you evaluate the limit as you approach that value for the slope, then you also get derivative. So just many, many ways of representing the derivative. And then the whole reason why I want to bring this up more so is I want to bring up this idea of differentiability. So very likely, if I had to take a guess, you're at some point on the test, they're either going to say differentiable or continuous. And so you need to know that differentiable means the derivative as you approach it from one side is going to equal the derivative as you approach it from the other side. That's what makes something differentiable. And so if you want to think about it in more common English, that's saying smooth, right? We were talking about cusps earlier. So you could have a cusp this way, right? We have a jagged edge. right? The derivative here is positive. The derivative here is negative. That's why it's not differentiable at that cusp. So we're going to go through a few different examples to show where things are not differentiable. So y'all should recognize this one as your V graph, right? So we just talked about the cusp. If you were to graph it, and you're allowed to use Desmos and stuff when you're taking the test this year, if you were to graph it, you'd see that at -3, you have a cusp here, and that you have two different derivatives, two different slopes as you approach that point, right? One is negative, one is positive. And then what happens for B? Well, B, when you graph the equation of a cube root function, you'll see that as you approach 0, the limit actually starts to approach infinity for the slope right there. And infinity does not exist. So here, this is not differentiable because you have a vertical tangent line. Let's call this a cusp. If we do the graph of C, the graph of C is the bird graph. What should we call this? Let's call this a kink. Right, what's happening here? Same reason, right? The derivative is different from the derivative. And then what about the last one? The last one, if we were to graph 10 minus x, let's pretend this is 10, right? It looks something like that. So at 10, let's see what happens. Well, in order for it to be differentiable, the derivatives have to be the same from both sides. So from the right side, there's a certain derivative. There's nothing here on the left side. So no derivative. No derivative. So these would be the reasons why a function or a graph is not differentiable. Questions on that one? So then we have these two theorems then. Right, so if something is differentiable, then it is continuous at that point. Right, you need to know that. And that's probably going to be the preface to your IVT. Like if it says a function is differentiable, then you can use intermediate value theorem. And then we also have the contrapositive. The contrapositive is also true. If f is not continuous at that point, then it is not differentiable, right? If you have to pick up your pen, then you can't take the derivative of it. Okay, and so this is where people mess up then. The question is, if something is continuous, then does that make it differentiable? Launch a poll to see who's still awake here. If something is continuous, must it be differentiable? No, everybody got it right, yeah. So you want to think of cusps, kinks, vertical tangent lines, right? So anytime you see this idea of continuity, maybe you want to think of those 4 images. Somebody fell asleep and hit yes by accident. Cool. So we have this idea here, right? So keep that in mind when you see differentiability. But know that only these 2 statements that I've highlighted are true 100% of the time. It can be differentiable, and that's another thing that they might trick you with on the test, the wording between can versus must. And then just in case you're curious, I don't think you need this bottom part, the symmetrical form definition of a derivative. I think that's beyond the scope of this. Really quickly, I want to give you L'Hôpital's rule. L'Hôpital with an S. You have these 2 indeterminate forms, right? 0 over 0, infinity over infinity. So if you want to evaluate the limit and it's impossible to do so, then all you need to do is take the derivative of the top and take the derivative of the bottom separately. I'll put this note here for people who are going to read it. Don't do quotient rule. I think that's the biggest thing that I see people mess up on when they get a L'Hopital rule question. They're like, oh, I'm going to do the quotient rule now because I can do that. No, take the derivative of the numerator and take the derivative of the denominator separately. Okay, so we have L'Hopital's rule right there. And so what I have is I have a couple of review questions that are high likelihood questions on the test. So we have this question: if the function is differentiable for all x, then what does a equal? So I'll give you a few minutes to ponder this. I'm gonna put up a poll. Let's see. Let's see. Yeah, I can put up a poll. Does it take over the screen if I put up a poll? Can you see it or can you not see it? Okay. I'll give you this hint. If f of x is differentiable, right, then we can use this. F of x is continuous. So we have limit as we approach x, 1 from the negative side. We can do direct substitution. Then we approach it as from the right side. Right, if the two functions have the same limits, right, they're continuous. So we go a minus 6 equals b plus 4. Or we can rearrange it and say a minus b is equal to 10, right? We can add that 6 over to both sides. This would be an equation. And then if it's differentiable, that means we have to set the derivatives equal to each other. So that's going to be the next step in this question. So we go 3a x squared minus 6. We can set that equal to 2bx plus 4. Right? We can evaluate now the limit as x approaches 1 for those. So we get 3a 1 squared minus 6 is equal to 2b plus 4. 3a minus 6 is equal to 2b plus 4. Oops, there shouldn't be a 4 there. Cannot take a derivative. You have to take the derivative of a number, and then it becomes 0. So we get what? 3a minus 2b is equal to 6. Then I can take this equation and do substitution or elimination, right? So I'm going to take everything times it by -2. So I get -2a plus 2b is equal to -20, right? Then I get a is equal to -14. The correct answer is B. Cool. And finally, one more question, and then you're all free to do whatever you want to do. Part C. This is actually from the AP exam, and it's asking you to use limit definition to figure out what f of 2 is and what f prime of 2 is. So they give you a function. It says f, g, and h are twice differentiable. Remember that differentiable means continuous. We know that now. Right? And then they give us the values of the function there, right? So it says the function h satisfies this really weird looking equation. And we know that the limit as x approaches 2 can be evaluating, look, they spelled it with the s, L'Hopital's rule, right? So use the limit of h of x to find h of 2. If we look at the function and it says it's differentiable, right? That means it's continuous and its value is 4. That means the limit as x approaches 2 of h of x should equal 4. Right? If that's equal to 4, then we can go ahead and plug in 2 into this whole equation and see what happens, right? So we get 2 squared minus 4 over 1 minus parentheses f of 2 quantity cubed, and it should equal 4. What's the problem though? Well, 2 squared minus 4 is 0, right? So 0 can't equal 4. So that means we're probably going to get indeterminate form, right? That's the only way the limit could equal 4. So because of that, we set the bottom equal to 0. We go 1 minus f of 2 quantity cubed, and we set that equal to 0 because of L'Hopital's rule. Right? Probably if you're doing this on your test, you need to say that you're using L'Hopital's rule. And then so if we do that, we actually get 1 is equal to f of 2 cubed, right? And then that just means f of 2 is equal to 1. Right? So this would be fair game on the test. There's not a lot of crazy calculations. And now what? Well, we have to use L'Hopital's rule now. So L'Hopital's rule says we use the derivative of the top and the bottom. So let's take the derivative of the top. So the derivative of the top is 2x. Derivative of minus 4 is 0, right? I forgot that last time. And then we take the derivative of the bottom. This 1, when we take the derivative, is equal to negative. We're going to talk about this more tomorrow, but we have to remember the power rule. -3 f of x, quantity squared. And then we have to remember the chain rule too. It's f prime of x. Right? So now we're going to use the limit as x approaches 2 of this function. And this limit should equal 4. So let's plug in 2, right? So we get 2 times 2, all of which over -3 times f of 2 squared times f prime of 2 is equal to 4. Right? So we know that the top of the function is equal to 4. So that means the bottom of the function has to equal 1 in order for it to work, right? So then we get -3 times f of 2 quantity squared times f prime of 2 is equal to 1. We know from our previous step that f of 2 is equal to 1. So we're going to replace that with 1. And if we go ahead and solve this, we get f prime of 2 is just equal to -1/3. And that's the answer for part C. Alita asks, why does it also equal 4 for the derivative equation? Because we established from the first step that the limit has to equal 4. Right, the limit of h of x is equal to 4. We couldn't find the derivative though, or we couldn't find the limit right now because in the original function, the top equaled 0. So it was in indeterminate form, right? So this is indeterminate form. You can't have 0 equal to 4. So then what did we do? We took L'Hopital's rule here. This part is L'Hopital's rule, and we had to use the derivative of the top over the derivative of the bottom. And then there's also part D, right? I just want to point out part D, just because you see this notation here, right? So just a reminder, when you have this weird notation with the g of x is less than k of x is less than h of x, that's going to be the squeeze theorem. Okay, so you could use squeeze theorem to justify part D. So that's all I had for you today. I'm going to give you a minute or so to ask any questions that you might have. I'm going to go ahead and upload my notes onto the Google Drive that you should have access to. There are a couple other limit worksheets. Like all these worksheets are on there. I only pointed out the problems that I thought were really, really important. If as extra practice, you want to do some of those worksheets and want to come in with questions tomorrow, feel free to do that. Got a question. What will constitute a 5 on the exam this year? That's a really good question. I think what will constitute a 5 on this exam will honestly be people who can truly write out explanations properly. I think that'll be a huge part of a 5. I think just by being able to do computations and taking derivatives, you can get a 3. I think it's those like little tiny nuances that'll split the difference between like a 4, 5 and a 3. That's why I'm focusing a lot on these concepts earlier on. Do you have homework? There is a limit review sheet that if you want, I'll upload it and I'll label it as homework if you want to do it. I think the biggest difficulty is that since this class time is so short and since there's so much to go through, I won't have time to review everything, but feel free to do the questions on that review sheet. And then if you have questions tomorrow, I'll spend the first like 10, 15 minutes answering questions. Another question, how are you going to show your work? You can either show your work on the test by writing it on paper. You'll have the chance to take a screenshot with your cell phone and upload it. Or all the questions can be answered by typing. So when somebody earlier was asking about, do we really need to know all these theorems? I'm like, well, if they're expecting you to be able to type everything, then yeah, they're probably going to have at least one answer that's going to require like a sentence or two in order for you to answer it. So you can either choose to write it out or you can choose to write it on a word processor like Google Docs or Microsoft Word. And can you upload a key? Yeah, I'll be happy to upload a key. Any other questions? Yeah, so what about all the fancy symbols? That's the thing, right? So they're not going to have a lot of fancy symbols. You won't need fancy symbols. Anything that can be input using a keyboard is fair game. So like integrals or square roots or like the 1/9 power, that's probably not going to be important for this test. So lots of A's and B's maybe. So you need to know AX plus B, AX minus B, that sort of stuff. That's going to be the most important stuff. So yeah, thanks y'all for participating. If you have any comments, feel free to respond to the email. I'll put my email up here really quick so y'all can email info@thinqueprep.com. Right, this is my first time doing a Zoom class as well. So any comments or things that you think could be improved, I'm more than happy to listen to that. And I'll leave this on for a minute or so. if any of you need to write it down. I'll also probably follow up via email because I have all your emails addressed. Alrighty, peeps. See you all tomorrow.